Today, we are diving into one of the absolute cornerstones of programming, loops. Seriously, this is the magic that lets a computer do all the heavy lifting for you, repeating a task over and over, thousands, even millions of times. We're going to break it all down, drawing from some great material from the World University of Bangladesh. Let's jump right in.
So let's start with the big question, right? Imagine you need to crop 1,000 photos, or maybe send a personalized email to every single person on a list of 500. You're not going to sit there and write the same lines of code 500 times. That would be insane. And that is exactly where loops come in. They are the engine that drives automation in pretty much all of programming.
So why is this such a game changer? Well, first off, it saves you from mind-numbing repetitive work. You write the logic just once, and the loop takes care of the rest. This makes your program way smaller, which is great, but it also makes it so much easier for you, or another developer, to read and understand. It's really the difference between a simple one-page recipe and a 500-page cookbook where every single page is almost identical.
Okay, so here's our game plan. We're going to cover exactly why we need loops, then explore the two main families they belong to. After that, we'll meet the three big stars of the show, the for, while, and do-while loops. We'll even check out how to jump in and out of them for extra control, and we'll wrap up by figuring out how to choose the perfect loop for your task.
All right, let's kick things off. Section 1. Let's really get into why this whole idea of repetition is so incredibly powerful in the first place.
At its heart, looping is just a structure that lets a piece of code run over and over again. But don't let that simplicity fool you. This isn't just for counting. This is how your music app goes through a playlist, how your social media feed keeps loading new posts when you scroll, how scientists process mountains of data. It's a fundamental building block of almost all modern software.
Now, here's where it gets interesting. Not all loops are built the same. They basically fall into two major families, and the difference is super simple but absolutely crucial: entry-controlled versus exit-controlled.
This little chart here lays it all out. On one side, you've got your entry-controlled loops, like for and while. Think of them as a strict bouncer at a club. They check your ID, or the condition, before they let you in. If the condition isn't met from the very start, the code inside might never run at all. Then, on the other side, you have exit-controlled loops, like do-while. They let the code run once, no questions asked, then they check the condition to see if they should do it again.
Okay, with that background, it's time to get our hands dirty. Let's meet the three most common loops you'll run into, especially in languages like C.
First up, the for loop. This is your workhorse. It's the tool you grab when you know exactly how many times you need to do something. And its biggest strength? How compact it is. The setup, the rule, and the update are all packed neatly into a single, easy-to-read line.
Okay, let's break this code down. The for loop jams three crucial parts into one line. First, int I equals 1. That's our setup. We're creating a counter called I and starting it at 1. Second, I less than or equal to 5. That's the rule. The loop will keep on running as long as I is less than or equal to 5. And third, I++, that's the update. After each trip through the loop, we add 1 to I. It's all right there, clean and simple.
And the result? Exactly what you see here. It prints the numbers 1, 2, 3, 4, 5, and then it stops. Totally predictable, totally clean.
Next on the list, the while loop. This one's a little more open-ended. Its whole philosophy is just, while this condition is true, keep doing this thing. And remember, it's an entry-controlled loop, so it checks that condition before the first run. If the condition starts out as false, the code inside is completely skipped. Now, let's look at the very same task, printing 1 to 5, but with a while loop instead. See how the structure is different? The setup, int I equals 1, happens before the loop even begins. The rule, I less than or equal to 5, is the only thing in the parentheses, and the update, I++, has to be put manually inside the body of the loop. It's a bit more spread out, isn't it? So what do we get? The exact same result. And this is a really important lesson in programming. There's almost always more than one way to solve a problem. The real skill is picking the tool that makes your code the easiest to understand. And finally, we've got the do-while loop. This is our exit-controlled loop, the act first, ask questions later member of the family. Its absolute superpower is that it guarantees the code inside will run at least one time, no matter what the condition is. Take a close look at the syntax here. The do keyword comes first, signaling do this action. Then you see the block of code. And where's the while check? It's sitting way down at the very end.
That's the secret sauce that guarantees that first execution. The code runs, the number gets printed, and only then does the program bother to check if it should do it again.
And there you have it. 3 different loops, 3 totally different structures, all giving us the exact same output for this simple task. It just goes to show you, choosing a loop isn't just about getting the right answer. It's about picking the right logic for the job.
But what if you need more fine-tuned control? What if you need to bust out of a loop early or just skip one specific part of it? Well, that's where jump statements come into play.
Think of break as your emergency exit. It yanks you out of the loop right away. Continue is more like a skip button for just the current route. And then there's go to. Now, go to is powerful. It lets you jump to basically anywhere in your code, but, and this is a big but, it can make your code an absolute nightmare to read and debug, so most modern programmers avoid it like the plague.
Here is a perfect example of break in action. The loop is supposed to run 5 times, right? But there's a little gatekeeper inside, an if statement that says, hey, if I is equal to 3, hit the brakes. The moment I hits 3, that break command fires, and the loop is terminated. Done. It doesn't even think about running for 4 or 5. And that's why the output just stops cold at 1, 2. Now, watch what happens when we swap break for continue. The setup is identical, but the behavior is totally different. When I equals 3, the continue statement tells the loop, you know what? Just skip the rest of this round and head straight for the next one. So it never gets to the print statement for 3. It just jumps to the update, I becomes 4, and the loop carries on. And that's why the number 3 is missing from our output.
So, after all that, we have all these different options. How in the world do you decide which loop to use and when? Well, it really just comes down to knowing their core strengths.
This table sums it all up beautifully. A for loop? It's perfect when you know exactly how many times you need to repeat, like if you're processing sales data for all 12 months of the year. A while loop is your best bet when the number of repeats is unknown. Think of a game that keeps running while the player still has lives left. And the do while loop? That's for when you have to run the code at least once, like prompting a user for a password before you can check if it's correct. You always have to ask that first time.
So, the main thing to take away here is that these are not just some abstract programming theories. They are real, practical tools for solving actual problems. I mean, think about it. Sending out a daily email report, your phone checking for new text messages, a website asking you to enter a valid email until you get it right, those are all loops. So what's a repetitive task in your life you could imagine automating with one of these?